Hi everyone, this is our 10th lecture. We're now in Unit 3. We're going to be talking about effect sizes today. The reason why we're going to talk about this specifically and have a whole lecture on it is because this is one of the core things that we're trying to get out of any regression model that we use. We usually want to understand what the nature of the relationship is and how important that relationship is. So today we're going to talk about effect sizes and we're going to define exactly what that means. So first, an effect size is anything that gives us information about the magnitude and direction of group differences or relationships between variables. So the question is, why do we measure that? Well, generally our research questions are asking, is there a relationship here or are there differences between these groups? But even if there is, so if we find that it's significant, we have a significant difference, we still need to know, is it meaningful? Does this difference actually mean anything in practice? Will this really change anything when people are actually intervening or changing something? Or is this a relationship that we should even intervene in? Those kind of questions can't be answered just with significance alone. Now, because there's a lot of overlap between these, I want to make this really clear. So when we're talking about effect size, the best term that I've found is meaningfulness. So it's asking how meaningful is the effect? And sometimes we want that in clinical terms or in practical terms. Conversely, statistical significance, that is talking about the evidence suggesting whether there is an effect in the population. So the effect size is telling us, is it meaningful? Significance is telling us, do we think it exists in the population or is it just showing up in this sample? But it's really important that we understand that these things don't tell us what the other one's trying to tell us. So for example, effect size, it doesn't tell us if an effect exists. Even if we find a large effect in our sample, that doesn't necessarily mean that the effect actually exists in the population. It might just be in your sample. Significance doesn't tell us the meaningfulness of the effect. So even if our p-value is super small, it's really significant, it still doesn't tell us if the effect size is actually meaningful. So it's possible, I don't know, I can't read your minds, but you might be wondering, why don't the p-values alone tell us that? Well, there's an important relationship between sample size, power, and p-values. To really understand, you have to remember what a p-value is, and to reiterate that, p-values are not a measure of the strength of the relationship between variables. Rather, it is talking about how crazy that result is if the null hypothesis is true. So for example, a p-value of less than 0.001, so something really significant, does not mean the treatment is much better than the control condition. Rather, it means it is very unlikely that the results we observed would occur if the null hypothesis, which in this case could be the treatment and control have the same impact, is true. So the null is always saying really no difference, and where the p-value already assumes that the null is actually true. That means all it can tell us is how crazy the result is, given the null is already true. It's not telling us how likely it is that the null is true or how unlikely it is. It is only telling us how crazy the results are if the null is true. So when the null is true, are our results really something we wouldn't see very often in that world? So one way to think about this is, let's say we stepped into a world where there was no relationship between the two variables. So the treatment is not working. Treatment and control have the same outcome. So we're sitting in that world. And we're taking a bunch of samples and we're just looking at in each sample what differences there are between treatment and control. Well, if a p-value is roughly like 0.001, that means extremely rarely would we ever see that result in that null world. We could definitely see it though. So even in the null world, we could find a difference that's big enough for the p-value to be really small. And that is one reason why it never tells us whether the uh, effect is real or not. It just tells you how crazy that result is given the null is true. So p-values are very confined to what they're telling us. It's very specific. So to really get better information out, we really need to know the magnitude of the effect of treatment. So we need to calculate an effect size. So I find when I'm teaching this class and other classes that people generally think of effect sizes in terms of like a Cohen's d or a correlation. And those are effect sizes. But effect sizes are much broader than that. So we need to kind of think about them in really a couple different ways. The first is really understanding the classes of effect sizes. So we have standardized and simple or raw effect size. So the standardized effect sizes describes the size of the effect and removes units from the variables. So you can think of standardized coefficients that we've used in this class. Cohen's d is a standardized effect size. The simple raw effect size, that is just describing the effect size, but maintains the original units. So think of just our regular coefficients. So if we watch more TV, what tends to happen to our income? Like the example we've used earlier in the class. That is just a raw or simple effect size. So for example, if you were examining the relationship between study time and hours and test scores and points, we could look at this in two general ways. We could look at a standardized and a simple effect size. So if it's standardized, one way we would look at this is you might conclude that for each one SD unit increase in study time, there is a 2 standard deviation increase in test score. What that means is we remove the original units of hours and points, and we're talking in terms of standard deviation increases. Most standardized effect sizes are going to be in those units in some form or fashion in standard deviation units. So we're not talking about hours and points anymore, we're talking about standard deviations, which makes it so we can compare that across variables and across studies. However, in this case, the simple or raw might actually be really interpretable too. For example, we might conclude that for each 1 hour increase in study time, there's a 5-point increase in test score. That alone could communicate quite a bit of information. So what are the pros and cons of standardized versus simple effect sizes? Well, for one, standardized, it's really good at interpreting the magnitude of effect when the units are not intuitive. For example, like an anxiety score. What does a 1 unit increase in anxiety score mean? Well, probably we don't really know. So using a standardized effect size can be really good in that case. Standardized is also for comparison across variables and studies, like I mentioned before. If we want to actually compare the results from this study to another one, standardized is really the only way that we can directly compare those or across variables. For example, we might want to compare something like hours studied on test scores versus is English your first language on test scores. It's really hard to compare a binary, is English your first language, and hours of study. But if we standardize, we're far more able to compare. However, when you're using power analyses, it's really important to keep in mind that standardized effect sizes can potentially be problematic when you're looking at at a power analysis. Another thing to note is a simple effect size is good when the distribution is non-normal, it's really far from normal, or when measured in a familiar scale like hours or dollars. When the distribution is really far from normal, then standard deviations become less reliable as a measure. So just using the simple or raw effect size can be really useful. Also, one note is do not standardize categorical variables. We already can get really useful information out without standardizing the categorical predictors. And we're going to talk about how in just a moment. So here's some effect sizes that you already know. So we have correlation, or R. We have R squared, adjusted R squared. We have coefficients. We have standardized coefficients. And you can think through which one of these are standardized and which ones aren't. Well, one of them, of course, the standardized coefficients, it's in the name, so that one is standardized. The coefficients, it doesn't have standardized in there, so maybe they're unstandardized. That is correct. Adjusted R squared, and R are all standardized. You can compare those roughly across studies because they're in the same units. But it's really important to keep in mind there's many different kinds. For example, we have Cohen's d, which most of us are familiar with ANOVA and t-tests and things. It can be obtained in simple regression when you standardize the outcome and have a two-level categorical variable. It'll just spit out a Cohen's d for you, or in other words, a standardized mean difference effect size, which is what a Cohen's d is. When there's covariates in the model, it becomes an adjusted Cohen's d or an adjusted standardized mean difference effect size. This is a really powerful way of highlighting, even when we control for some stuff, here's our standardized mean difference or adjusted Cohen's d. So we're going to prove it really quick using the data on Married at First Sight. We're going to use a simple regression predicting the relationship length, which is your outcome, based on the love expert couples worked with on the show, which is a dichotomous categorical predictor. So it's just a two-level predictor. And if we run this where we standardize the relationship length, our estimate is 0.191 between the difference between the experts. We can run the Cohen's d function on the same regression and we get the exact same thing. So when it's a simple regression, when we standardize the outcome and we have a two-level predictor, what it's spitting out is just a Cohen's d. If we have control variables in there, then it becomes an adjusted Cohen's d. We're adjusting for other variables. So there's others. We have eta squared, which is essentially R squared. Eta squared is used with ANOVA. We have odds ratios, which we'll learn about in logistic regression in a couple weeks. Again, all of these are just trying to tell us the effect size. How big is the effect? How big is the relationship? So ultimately, the core idea here that I really want you to understand is that effect size is anything that measures the size of a relationship between variables or a difference between groups. There's loads of ways we can do it. There's a lot of common ways. We've talked about a lot of those today. But remember, anything that measures that is, by definition, an effect size. So the question may come up, which effect size should I actually use in my study? Now, different effect size measures are better suited for different situations. So with categorical variables, you do not want to standardize the categorical variables and the outcome. And sometimes if your outcome is in interpretable units, you may just want to do raw, simple effect size where you look at the difference between groups on income or something. If you have unbalanced group sizes, there's going to be potential issues with certain types of measures. What I would recommend is using a standardized coefficient there. So if you have unbalanced group sizes, the standardized coefficient will still give you useful information. It'll tell you the difference in standard deviation units. Now note when it's unbalanced that the bigger groups are going to dominate the standard deviation measure. As the groups get really big when the other one gets really small, the small one doesn't have as much influence over the standard deviation measure, and so the difference is going to be more in terms of the information from the bigger groups. Now, if you have lots of variables, you may not want to do a Cohen's d or a correlation because there's going to be a ton of numbers. But there's things like R squared that can be really useful in cases like that because it can give you the amount of variance that all the variables together are explaining of the outcome. And then when it comes to ordinal data, like Likert scales, there's certain things that we either have to assume that, first of all, either it's a continuous scale or we need to treat it in a different way, like a categorical variable, and use those kind of effect sizes. But again, each of these, it's really going to come back to what's your research question? What do you really want to know? Are you really interested in the difference between two of the groups, and maybe a Cohen's d between just those two groups is important? Are you interested in how all the variables together explain the outcome? Then maybe an R squared. So again, you really have to think through, what do we really want to know? So the general interpretations of effect sizes, when Cohen and other statisticians have made recommended effect size interpretations like what's small, moderate, and large. But these are fairly arbitrary. But it's important to keep in mind that these can vary based on a number of parameters and they're highly dependent on your field of study. For example, an R of 0.3 may be huge for one field, but really disappointingly small for another. So in order to really understand what is big and what is small, you really need to gain an understanding of what is considered standard in your literature for a small versus large effect. This applies to both the standardized and the simple effect sizes. For example, some really simple comparisons with our GSS data set suggest that women earn less than men by about $5,000 per year. Now, if we want to understand if that's big or small, we may want to understand other countries. Is the difference between men and women in other countries really big or small? You may want to understand other factors like racial differences. And then you can say, well, this is really big compared to what we've seen in other countries or other situations. Also, the valid interpretation of an effect size, again, comes back down to the assumptions of our model. If we don't have a good model, then our effect size is not going to be valid. It's not reliable. So we need to check the assumptions of our regression. And this is a good moment to think, do I remember what the assumptions of regression are from our lecture on that? Another one is the reliability of the measurement of the variables. If you remember our discussion about measurement error, if your measures aren't good, then your effect size measure isn't going to be good either. And you need to consider, is the sample, or are the methods, is the design, or all those things generalizable? If we have a very particular sample that has a lot of weird attributes, we used weird methods or novel methods, or our design was unique, then we might not be able to generalize our effect size that we found to other studies or other situations. So sometimes our effect size is really just telling us the difference or the relationship that we've seen in our specific sample. If we use really good methods and good measures, our assumptions are met, then we might be able to generalize and say this likely applies to the rest of this population. So to finish, let's try an example. So let's go back to the married at first sight data. So you decide you want to know whether couples who have more satisfying relationships, which is a numerical predictor, tend to earn more money, which is your outcome. You also want to control for their location, which is just a categorical variable. You start off running an unstandardized multiple regression. And let's say these are the results we got. So we ran income predicted by marital satisfaction and location. And we have a couple of significant variables. So we have satisfaction, and the location, New York City, is different than the reference group. So what does this mean here? For the satisfaction variable, we would say for each 1 unit increase in relationship satisfaction, there's an associated $9,698 increase in couples' combined income controlling for location. So again, we're controlling for location, but we're finding this relationship, and we're interpreting this in simple, raw effect size units. So we're saying a 1 unit increase in relationship satisfaction, there's a 10 grand almost increase in couples' combined income. One question that may come up is, what exactly is 1 unit increase in relationship satisfaction? Is that a lot? Like, is that hard to obtain, or is that easy? And maybe we have that information and we can describe that, and this will be perfectly interpretable as is. But it's quite possible that we also don't have that information and we're not totally sure. So this may not be the most useful form of understanding the relationship here. We also can look at the categorical ones where we have, on average, couples living in Dallas earn about 6 grand more than couples living in Atlanta, which is the reference category, controlling for relationship satisfaction. And on average, couples living in New York City earn about 23 grand more than couples living in Atlanta, controlling for relationship satisfaction. In my mind, those two categorical ones that we compared make a lot of sense as is. It's very intuitive to understand that people in Dallas tend to earn a little bit more than in Atlanta, and couples in New York City tend to earn quite a bit more than people in Atlanta. But again, what does a 1 unit increase in relationship satisfaction mean? So we could increase our interpretability, at least for that variable, by standardizing our numerical variables. Remember, we don't want to standardize a category. And we could get the following. So we have a standardized income and standardized marital satisfaction, and then just our regular location variable. When we do that, again, we have a significant relationship. No surprise, because doing standardization doesn't change the significance of our variable. It just changes the units of our effect size. So here we have 0.812 is our coefficient on our standardized version of satisfaction. So we can interpret that as, for a 1 standard deviation increase in relationship satisfaction, there is an associated 0.812 standard deviation increase in combined income, controlling for location. What's interesting about that variable then, that effect size, is that is similar to a partial correlation. So for a 1 standard deviation increase, we're seeing almost a 1 standard deviation increase in income, which is really big. We can see that as, if we make a pretty big jump in relationship satisfaction, we're also going to make a pretty big jump in combined income. That's telling us these are pretty closely related to each other. We also can get information out of the other ones, but I believe our previous example was more interpretable than talking about couples living in Dallas have a combined income that is 0.09 standard deviation units higher than couples living in Atlanta. I think that is less interpretable than just saying couples living in Dallas earn almost $6 grand more than couples living in Atlanta. What's cool with regression is you can report both of these. You don't have to just pick one and go with one, but you can report both. And that can provide even more information about the relationships happening here. With that, here's some resources to look at. They describe effect sizes in general. They compare standardized and unstandardized effect sizes. And there's this really in-depth explanation of effect size with interpretation at this website here. So please take a look. These are great resources and can help you fill in any gaps that still remain from this lecture.